Hello and welcome. In continuation with our complexometric series, where we were discussing about photometric titrations in our previous lecture, photometric titrations are also a part of complexometric titrations, which can be done with or without an added indicator, as we have discussed earlier. And we were discussing the example of copper sulfate solution at a particular pH, wherein as the titration proceeds, the intensity of the color increases and hence the absorbance value also increases. If, however, copper is titrated in an ammoniacal medium where the color of the solution is deep blue due to the formation of tetramine complex, which has a high absorbance, then during the titration copper EDTA complex forms, which is of much lighter color, and the absorbance decreases gradually. So this is in contrast with the earlier method. In this case, copper is taken in an ammoniacal medium wherein copper forms tetramine copper complex, and tetramine copper complex is deep blue in color. If this complex is titrated with EDTA, then the tetramine copper complex will start breaking and copper will be forming a complex with EDTA, as a result of which the deep blue color will start lightening, and as a result of this the absorbance, which earlier was high in the high intensity color of deep blue, now starts decreasing because copper EDTA complex is of much lighter color. So absorbance decreases as the intensity of the color decreases. A metal which does not show a color change during complex formation can be titrated directly by the addition of another metal ion which does show a color change. That is, for example, bismuth can be titrated with EDTA if some copper is added, and this is because when bismuth forms a complex with EDTA, it does not show any color change. Bismuth EDTA complex is colorless. However, if some copper ions are added in this particular solution, then the titration of bismuth and EDTA can be carried out as a photometric titration because copper EDTA forms a colored complex which is light blue in color, and that can be used for the estimation of bismuth ions. Another method in which we were discussing about photometric titrations is the titration with an added indicator. If an indicator is present during the titration with EDTA, the metal is complexed with the indicator. The absorbance will vary according to the color of the metal indicator complex and that of the metal EDTA complex. The more intense color will give a higher value of absorbance, and this is an example, as we have said, where the titration with an indicator is chosen, and this indicator complexes with the metal, and once the indicator forms a complex with the metal, the color of the metal indicator complex, depending upon the intensity, gives a particular absorbance value. Upon titration with EDTA, the intensity of the color will either increase or decrease, and accordingly the absorbance value will increase or decrease, and that absorbance value can be measured to give the amount of the particular metal ion in the solution by a series of graphs, and the more intense color will give a higher value of absorbance. Complexometry has a number of applications in which we will be discussing a few of them. A widely used application of complexometry is the determination of calcium and magnesium, as in particularly hardness of water, or simply a solution in which calcium and magnesium are present in combination with each other. This process is very simple, so leads to wide acceptance of EDTA as the complexing agent in most titrations. A sample of calcium and magnesium is titrated in one portion of the sample and calcium is titrated in the further portion. This is a case where both calcium and magnesium are in one particular solution using eriochrome black tea as the indicator. In the portion where calcium needs to be titrated is alkaline, where magnesium gets precipitated as its hydroxide. This, in a way, we are talking about masking, as we have discussed earlier. When only calcium has to be determined, then the solution is made alkaline, magnesium gets precipitated as magnesium hydroxide, and calcium can be further titrated using the indicator. Calcium is estimated alone. We have a total of calcium and magnesium earlier. Subtracting these two values gives the amount of magnesium ions in the sample. As we have said, magnesium is then calculated from the difference. Although this procedure is very simple, but many difficulties can arise in its practical application. The amount of magnesium present in the sample is less, which is a hindrance for the successful application of this procedure. That is, always in any particular sample, either hard water or any mixture of calcium and magnesium, the amount of magnesium will always be less than calcium, which becomes a bit difficult for the application of this procedure. Precipitation of magnesium hydroxide can result in the co-precipitation of calcium also to some extent as calcium hydroxide. Although magnesium hydroxide precipitates first and its insolubility product is much less than calcium hydroxide, but still once alkaline medium is created, magnesium hydroxide can precipitate, and along with that, co-precipitation means along with the required precipitate, calcium can also precipitate as its hydroxide, thereby decreasing the concentration of calcium in the solution, causing an error. This can, however, be prevented by adding EDTA in excess and then precipitating magnesium. As a result of excess EDTA, calcium complexes with the EDTA and co-precipitation of calcium can be avoided. Since the calcium EDTA complex is much more stable and calcium forms a complex with EDTA faster than magnesium, therefore, if excess of EDTA is added, then that particular calcium ion in the solution will complex with EDTA and the co-precipitation can be avoided. After this, the solution is then filtered and the excess of EDTA is back titrated with a standard solution of calcium, and this back titration is necessary because some of the calcium has complexed with EDTA and that also needs to be estimated. The calcium EBT complex is very weak, so it breaks upon the addition of even a drop of EDTA. This happens especially in the presence of magnesium. And why it happens especially in the presence of magnesium? Because the magnesium EDTA complex is less strong, but the magnesium indicator, to be specific, magnesium EBT complex is stronger than the calcium EBT complex. The use of new indicators like chalcone, the structure of chalcone can be seen in the adjoining figure, for calcium can solve this problem, which give sharper endpoints. So instead of using eriochrome black tea for calcium, we can use chalcone as the indicator for the estimation of calcium, which gives a sharper endpoint. But in case where magnesium is also there and calcium is also there, in that case EBT has to be used as the indicator, because chalcone as the indicator will not give a color change for magnesium. It is not a suitable indicator for magnesium. Calcium can be titrated only in highly alkaline medium, that is a pH of 12. So, EBT or muroxide cannot serve as good indicators for its determination. But we have already seen that EBT is used as an indicator for calcium only when it is present along with magnesium. If calcium has to be estimated alone in a solution, then the preferred indicator is chalcone. Calcium along with magnesium can be estimated using EBT by the methods which we have discussed earlier. The stability of the magnesium indicator complex is greater than calcium indicator complex, and the indicator over here being EBT, and this is specific for the case where magnesium and calcium are in combination with each other. The stability of the magnesium EDTA complex is less than the stability of the calcium EDTA complex. The above is the basic principle behind the EDTA titration of a calcium and magnesium together. Another application of complexometry is the determination of hardness of water. So, permanent hardness is determined by titrating the sum of calcium and magnesium ions and expressing them in terms of calcium using iriochrome black tea as the indicator. So, first the total amount of calcium and magnesium ions are estimated in a particular hard water sample, and the hardness is determined in terms of ppm of calcium using EBT or iriochrome black tea as the indicator. And iriochrome black tea is being used because here both calcium and magnesium are present together. For this determination, magnesium EDTA complex is added to ensure a sharp end point. This is because the calcium EBT complex is very weak and will break upon the addition of a very small amount of EDTA. As we have seen in this previous slide, the calcium indicator complex is very weak, which breaks on the addition of a single drop of EDTA. So, the known amount of magnesium EDTA complex when added results in the formation of a magnesium iriochrome black tea complex as soon as it is added to the solution of calcium and EBT and buffer, as magnesium EBT complex is stronger than calcium EBT complex. So, what is done is that in a conical flask, hard water is taken in a particular volume, and then the iriochrome black tea is added after the addition of the buffer solution, and some amount of magnesium EDTA complex is also added, and this amount which is added, although small, is a known amount. The moment the magnesium EDTA complex is added to the conical flask, magnesium forms a complex with iriochrome black tea immediately, since magnesium iriochrome black tea is more stable than calcium iriochrome black tea. So, the calcium iriochrome black tea complex breaks and magnesium of the magnesium EDTA complex goes and forms a complex with EBT, and then the titration starts, wherein the free calcium starts complexing with EDTA first, since calcium EDTA complex is stronger. Once all the calcium ions have complexed with EDTA, then the magnesium EBT complex breaks and EDTA starts forming complex with magnesium, and this continues till the reaction is complete, wherein the end point is from red to blue. So, when the calcium EBT complex forms, the calcium is free and starts complexing with EDTA. This gives a sharp color change at the end point, and again as we have seen that the magnesium indicator complex is more stable than the calcium indicator complex. Therefore, it forms a complex with the indicator more fast than calcium, and magnesium EDTA complex is less stable than the calcium EDTA complex. Therefore, calcium forms a complex with EDTA first upon titration, and when all the calcium ions have exhausted, then only EDTA forms a complex with magnesium. So, this is the basic principle behind the EDTA titration of calcium and magnesium together as discussed already. For the determination of hardness of water, 0.01 molar of a standard EDTA solution is taken. A buffer solution of pH 10, magnesium EDTA complex, a pinch of EBT indicator, KCN, potassium cyanide, and a bit of ascorbic acid is required. So, to 10 ml of tap water in a conical flask, tap water which we are assuming to be hard water, 3 ml of buffer is added, then 3 ml of magnesium EDTA solution is added, a few crystals of KCN and ascorbic acid, and a pinch of Erythrochrome black tea is added. This solution is titrated with EDTA till the color changes from red to blue. KCN and ascorbic acid mask the calcium when magnesium ions are being estimated. So, this is the role of KCN, potassium cyanide and ascorbic acid which has been added. For low amounts of hardness to be measured, large volumes of water samples may be needed. So, to summarize whatever we have discussed in the previous lectures, the requirements for a complexometric titration to proceed are that the complexes formed should be stable, steps involved in complex formation should be minimum, and the complex reaction should be stoichiometric. A monodentate ligand, bidentate ligand is the one. A monodentate ligand is the one which has one donor site. A bidentate ligand has two donor sites, and so on. And in this case, EDTA is a hexadentate ligand which has 6 donor sites, which we have seen already in its structure. A chelate is a 4, 5 or 6 membered ring complex formed by polydentate ligands. Rings with fewer number of groups possess strain, so are lower in stability. The greater number of members of the ring also result in lower stability because of entropic effect. So, a chelate which is stable has either 4, 5 or 6 membered rings. EDTA forms 1:1 complex with all metal ions, and that is because EDTA is a hexadentate ligand. It having 6 donor sites can satisfy a maximum of 6 coordination sites of a particular metal ion. So, one ligand or of EDTA is sufficient to complex with many donor sites or many coordination sites of the metal ions. The gain in stability of a complex by replacing monodentate ligands by a single n-dentate ligand is called chelate effect. A zwitterion is a structure where both positive and negative ions reside on the same structure, and this structure can be seen for EDTA, wherein both positive and negative ions are on the same structure, and the structure we have already seen in our previous lectures. Copper and nickel form colored complexes with EDTA. Generally, many other metals do not form colored complexes. A solution must be well buffered during EDTA titration, because during the titration, the pH of the solution decreases due to the release of H plus ions from EDTA. So, to increase the pH of the solution, Since the indicator gives color change at a pH 10, buffer is added, and this buffer is generally a solution of ammonia and ammonium chloride, because this particular buffer has a pH of 10. pH 10 is necessary for the indicator, that is iriochrome lacti, which we are discussing, to give a particular color change. A metallochrome indicator is an indicator which gives color change on complexing with a metal ion. So therefore, iriochrome lacti, muroxide and a number of indicators, PAN, etc., which we have studied, are all metallochrome indicators because they give color with the metal ion. A metal indicator should form a complex with the metal, but this complex should break upon the titration with EDTA, and that is the basic requirement for a titration to proceed, because if the complex does not break, if the metal indicator complex does not break, then the titration will not proceed, the metal will not form a complex with EDTA, and the metal EDTA complex should be more stable than the metal indicator complex for a complexometric titration to proceed. Iriochrome lacti indicator undergoes color changes from red to blue to yellow at a pH range 6 to 12, and what we are requiring here in our titrations is a color change from red to blue only. So the pH will be required between 6 to 10, or to be specific, a pH of 10. Iriochrome lacti cannot be used as an indicator in acidic medium because its phenolic hydrogens will not dissociate in acidic medium. As we see in the structure of iriochrome lacti, it has two phenolic hydrogens which will not dissociate if the titration is carried out in acidic medium, and if the phenolic hydrogens do not dissociate, then EBT will not be able to give a color change from red to blue, because red color is due to the undissociated indicator, blue color is due to the dissociation of two phenolic hydrogens of iriochrome black tea. The blocking of an indicator does not allow the complexometric titration to proceed, and this blocking may be due to the formation of strong complex between the metal and the indicator, and this strong complex will not break no matter how much amount of EDTA we keep on adding for the titration. So if the metal indicator complex does not break, then that is termed as the blocking of an indicator. The masking of ions needs to be carried out if two metal ions need to be titrated in presence of each other. Masking is a process where one of the ions is kept in a dormant state and the other ion reacts with EDTA, and this masking is needed where two metals are titrated in presence of each other. Disodium EDTA is used to make solutions of EDTA in water. EDTA, we all know, is an organic ligand which is insoluble in water. However, its disodium salt is soluble in water, and for that matter all sodium salts of all metal ions or all ligands are soluble in water. So its disodium salt is used to make solutions. Many other types like back titration, replacement titration, etc. can be carried out to titrate those metals with EDTA which do not have a suitable indicator to observe the color change. Copper cannot be estimated in a solution by titration with ammonia solution, and this is because of the fact that copper and ammonia follow a stepwise reaction wherein 4 steps are required, in which ammonia molecule attaches one by one in each step till all 4 ammonia molecules have attached to copper to give a tetramine complex. So since this is a stepwise procedure, a long procedure, so therefore this titration of copper cannot be carried out with ammonia solution. Instead, copper can be titrated with EDTA, wherein copper EDTA gives a colored solution, and it is termed in case of photometric titrations. Many impurities can be found in distilled water, especially the presence of calcium and magnesium ions, which can be a source of error in EDTA titrations. Apart from these, alkalimetric titrations can be carried out with EDTA, since when a solution of disodium EDTA, which is also termed as Na2H2Y, is added to a metal ion solution, a complex is formed with the liberation of two protons, as is seen in the following equation, where a divalent metal ion combines with EDTA to give the metal EDTA complex My, where Y stands for EDTA, H2Y2 negative stands for the two dissociated proton EDTA ligand, and along with this two protons are released. These protons or H ions which are set free can decrease the pH of the solution, and that is why we are using a buffer to maintain the pH. These protons which are set free can be titrated with a standard alkali, that is maybe an NaOH solution or sodium carbonate solution, by the usual acid base titration using either phenolphthalein or methyl red as the indicator. Deionized water free of all polyvalent ions should be used for all the estimations. The titrations should be carried out slowly towards the end point, wherein the reddish color should totally disappear at the end point. So, the titration should be carried out very slowly. The EDTA should be first added dropwise, and then the titration should be proceeded in a slow and steady manner, so that the end point is sharp. The pH of the solution should be maintained using a buffer and not adjusted by pH meters, and this is because the pH meter is only used to adjust the pH of the solution. One can simply adjust the pH of the solution to 10 using an instrument, a pH meter, but as the titration proceeds, the pH will again start decreasing, and it again has to be maintained by a pH meter. So, to increase the pH and then further maintain it also, a buffer solution is to be added for all kind of complexometric titrations. Thank you.